Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can factor special products of polynomials. So we are going to start by talking about a couple different types of special products. The very first ones we're going to look at are perfect square trinomials. Now notice how these ones are trinomials, which means there are actually going to be three parts. And so what we look for when we're looking for a perfect square trinomial is one where the first term is a perfect square and the last term is a perfect square. If both of those are perfect squares, then we have a perfect square trinomial. And what we can do is we can break it down with the first square and the second square. Now what makes a difference is the middle term here. So as we look at our middle term, notice how this one is positive. So if our middle term here is positive, then what happens is our middle term over here will be positive. If our middle term is negative, like you can see down at the bottom here, then what will happen is our middle term right here will be negative. So we really want to take into account what those signs are and use them to then solve the problem. So let's take a look at a couple of examples of perfect square trinomials. So this first one here that we want to factor, we notice that this first term is a perfect square and this second term is a perfect square. This one is n times n. This one is 4 times 4. Our middle piece is 2 times n times 4. Now notice that's a very special characteristic of these perfect square trinomials is that middle term is 2 times the first term times the second term. And so because that's the case, we know this will factor into n plus 4 squared. And that plus comes from this plus right there. Now let's take a look at this one. This one also is a perfect square trinomial because the first term is a perfect square. It's 2x times 2x. And our second term is a perfect square. It is 3 times 3. So because those are both perfect squares and our middle term here is 2 times 2x times 3, what we can do is write it as 2x with a 3. Then we look at our sign here. Because it's a subtraction sign, it's going to be minus 3 squared. Awesome. Okay, so let's try one more example like this. Again, we're going to look at that first term and the last term. Are they both perfect squares? In this case, yes. The first one is 4x times 4x. The last one is 7 times 7. So as we have both of those, we can double check to make sure that this middle term is 2 times the first times the second, and it is. And so because of that, and with our plus sign, we know this will factor into 4x plus 7 squared. So that's how you would factor a perfect square trinomial. Again, check the first term to see if it's a perfect square. Check the last term to see if it's a perfect square. If they both are, regardless of what the middle is, as long as it's 2 times the square times the first one times the second one, we will have a perfect square trinomial. Now, another type of special product that we're going to look at here is the difference of squares. So the difference of squares is where the first term is a square and then we subtract another square number. Now this number can either have variables in it or not. So let's take a look at a couple of examples here. So this very first one, x squared minus 25. Well, this is actually a perfect square. X squared is x times x. 25 is perfect square, 5 times 5. So what this actually factors into is the first plus the second times the first minus the second. So this will become x plus 5 times x minus 5. And the second one, we can do the same thing. 4z squared is the same as 2z times 2z. And 1 is the same as 1 times 1. Those are both perfect square numbers, so we can actually write this as 2z plus 1 times 2z minus 1. Awesome. Okay, now sometimes they're going to look like perfect squares. Sometimes we might see something that doesn't look like a perfect square, like 2 and 50. But remember when we go through and factor polynomials, we want to factor out the greatest common factor first. So in this case, what is our greatest common factor here? What's a 2? So I'm going to factor out a 2, and I end up with m squared minus, not 50, but 50 divided by 2, which is 25. And so now that we have this, we actually have a perfect square inside. This is m times m. This is 5 times 5. So then as we factor it out, we end up getting 2 m plus 5 times m minus 5. Awesome. This second one can do the same thing. We're going to factor out a 3 there, and we end up getting x squared minus 16. And this factors into x times x. This one breaks down into 4 times 4. So we really get x is 3. 3x squared minus 48 is 3 times x plus 4. Times x minus 4. Awesome. So that's kind of how we can use this difference of squares. Now, sometimes we can use that difference of squares when we notice something else. So sometimes we'll run into problems that are actually to a power bigger than a square. We might see something like 64x to the 4th minus 81. Interesting, right? Now this is an x to the fourth, but it's actually a square because this breaks down into two square numbers, right? This is the same as x squared times x squared, and this is the same as 9 times 9. So we can actually break down, even though this is a fourth and this is a fourth, we can break those down into perfect squares, and this actually equals 8x squared plus 9 times 8x squared minus 9. So the difference of squares doesn't only apply when the number is a square, like the number itself is just a square number, as well as the variable is x squared or m squared or something like that. If the whole term can be square rooted, is a perfect square. So an x to the fourth, an x to the ninth, things like that, then we can actually break it down using that difference of squares, which is super cool. Okay, the last type of properties that we're going to talk about are the sum and difference of cubes properties. And what we do with those is we actually use oftentimes an acronym called SOAP. And this acronym that we use helps us decide what the signs are going to be when we do the problem. So notice how we have both the sum and the difference. So both of them follow this rule. The SOAP is for our signs. Again, don't forget that. And SOAP stands for same, opposite, always positive. Positive. Okay, same, opposite, always positive. So how does this help us? Well, notice this first one. We've got a cubed plus b cubed. Well, that really factors into a plus b, same sign, times a squared minus, oh, not 2ab. That is a trick there. Minus just ab. Oh, glad that we got that. Minus ab plus b squared. So notice how our signs there decided to stay same, opposite, same. And that's what we care about there. Oop. Okay, so notice the same thing happens when we have a subtraction sign in the middle. We have a subtraction, so our first term has a subtract in it. Then we have a plus, and then the last one, again, is always positive. So let's go ahead and practice using these here with these different things. So again, remember, we're going to have the first, the second, the first squared, the first times the second, and then the second one squared, right? And then our signs follow SOAP. So let's go ahead and break this one down. 8x cubed is actually going to be 2x times 2x times 2x. 1,000 breaks down into 10 times 10 times 10. So as we break down these factors here, we can then put it into our pattern, and we end up getting 2x, same sign, plus 10, times 2x squared, opposite sign, 2x times 10, always positive, 10 squared. And then we can simplify this, and we end up getting 2x plus 10 times 4x squared minus 20x plus 100. Fantastic. So that's kind of how it'll work. We'll do the same thing with this one. This one breaks down into 3x times 3x times 3x. This breaks down into 2 times 2 times 2. So then as we factor this out, we get 3x, same sign, minus 2. 3x squared, which is 9x squared. Opposite sign, which is plus. 2 times 3x, which is 6x. And then always positive, 2 times 2 is 4. Fantastic. So that is kind of how we would do that. Again, just like we could before, we can also look for greatest common factors to see if we can pull anything out. So in this first case, do we have a greatest common factor? No, I don't see one. And so I'm just going to break this down like we always do. We've got a 4x times a 4x times a 4x. And we've got a 5 times 5 times 5 here. And an easy way, remember, to check if we have a perfect cube is to cube root it and see if it comes out as a square, as a cubed number, right? As a whole number, an integer, things like that. So as we have cubed root these and figured out what we have, we're going to follow that pattern. So 4x, same sign, plus 5. 4x squared is 16x squared. Opposite sign, 5 times 4x is 20x. Always positive, plus 25. Perfect. Now this one right here, the first number is not a perfect cubed, neither is the second one. So I'm going to factor out a common factor there, and the common factor I'm going to factor out is a 2. So once we factor out a 2, what we end up getting is 27x cubed minus 8. And we actually did that problem on the previous page. And so we know that that's going to factor out into 3x minus 2, 9x squared plus 6x plus 4. Fantastic. So that is how we can factor those. Again, all of these patterns are super cool. We did just talk about 5 different ways that we can factor using special product patterns. And using these patterns, it's so helpful because then we don't have to try to break it down, find numbers that go into it. We can observe that this is the pattern, especially with those binomials, and apply the pattern directly. And again, remember, just like we saw with this example here, it doesn't have to be a square in the sense of an x squared or an m squared or something like that for us to apply these rules. If we have something that can break into a square, is a perfect square number, then we can use that difference of squares. If we have something that's a cube, we can use that sum or difference of cubes. As long as it applies to both of them, it will always work. So keep that in mind as you go through and use those special product patterns, but that is how we can use special products to factor polynomials.